Let's get started. Okay. So if I remember correctly, just remind me if not. We did this last time. So what we did is we had a problem like this, right? We had a problem like this, and this guy goes rotation, right? This is spring rotates, and this guy rotates, and this guy rotates, everything rotates as shown in the picture here. As shown here, right? This is how they rotate. So during the rotation, so we got we got three different terms here. One from this, one from this. So K is this guy. K is this guy, right? This is K. And D, this D is this guy here. Then similarly, you have T here. So T, oops. So T is this guy here. And inertia is this guy. Inertia is this guy here. Okay, so we got all four of them and set that to 0. So that gave us this equation. So this is what we did last time, right? Now, what I'm trying to say today is this. All right, let me go back one more time to this picture. And so, all right. So can I simplify this here? Can I simplify this? If I simplify this, what did I get? In the, if you remember, d s theta s plus k s theta s plus j s square theta s ts. Did you see that? This is what you get. So how can I, let me combine this, let me factor theta s out. So js square, let me begin with the highest order. So js square ks, oops, why did I say ks here? I made a mistake. So ds, right?
I was about to ask that, where that came from.
Okay, thank you. Yeah, plus k. So theta s equals ts, right? So in the beginning, I said you'll be excited about this today's lecture. You know why? Because even doing this, without doing this, you can simply write this. What do I mean by that? What do I mean by that is this. So what is on the left hand side? Sum of impedance connected to motion at theta 1. So this is what I meant. So this is theta, right? How many theta do we have here? Only one theta, right? Okay. So add all the impedances together without worrying about the sign of those guys. Don't worry about anything because we have theta, right? One theta. So add all this together. So what is this guy? This is K. This is ds. This is js square. Add all this together. Js square plus ds plus K. Then times theta s equals, then your right hand side is always sum of square of all the torque. Sorry, sum of all the torque. So what is the torque here? Just only one torque. Guys, question here.
I have a quick question about the beginning of the equation, where it says that that lowercase j is counterclockwise. Why do we have a negative out in front of it? I know that it's just going to wind up turning positive anyways, but Is that just because that's what, uh, sorry,
Go ahead, go ahead.
is that like the tables that we have? Is that just what it says J is? Is it always just negative, and since it's counterclockwise, we add that negative to make it positive?
Yes.
Okay, okay, thank you.
So what I meant is this. So since theta is clockwise, okay, this negative reflects this negative meaning clockwise, okay? So theta increases clockwise, that's why you have negative here. Remember, clockwise is negative?
Right.
That's why. So I wanted to match this guy with this. So summation torque minus J alpha equals 0, right? This is DL number, principle, right? You know what? Right now, I'm kind of sometimes regret that. Why did I tell you guys do DL number? You should have done, you know, Newton's law. It will just give you same answer anyways. So if you don't like DL number, you can do this Newton's law also because they are same anyways. I know they are different physically, right? So when you interpret it, they are different, right? But mathematically they are same. Okay.
Okay.
So either you can do DL number or you can simply say Newton's second law.
So are you kind of saying that because we only have the one external torque, that all the torque for all the other elements is going to be the opposite sign? For like the spring, the hash pot, the inertia, all that is going to be opposite to the external torque?
Opposite to external torque, no. So in this equation you said T minus J alpha. You are talking about this minus sign.
Oh, okay, okay.
I'm afraid I answered the question.
It's okay.
Can you clarify a little bit?
Well, I'm just noticing that the signs for all of the reaction torques is opposite to the external torque, which is clockwise, but all the, for the reactions, they're all counterclockwise.
Oh.
So I'm just noticing that.
Yes.
That's just
You're right.
but if you were to have, multiple external torques, maybe two in different directions, like then it wouldn't always be just opposite. That would make it more complicated. But for this,
In that case, Jane, that's a good point. In that case, no matter how many degrees of freedom you said, it could be T1, T1 theta 1, T2 theta 1, theta 2, and so on and so forth. It means we are talking about 2 degrees of freedom. So in that case, remember we just we just stay in the inertia here, and we just examine our surrounding, just adjacent, right?
right, yeah.
So we'll do that, and we'll add them together eventually.
Okay.
Quick question. What chapter is this again? 2.6 or 2? Is this chapter 2?
2.6.
2.6. Okay.
Jen, did I answer the question?
Yeah.
Okay. Now, how do you like this guy? Like, we had to consider all those, remember we had to consider all those sign into account. We had to be careful about those sign, right? See, okay, this is positive, this is positive, this is negative, this is positive. We had to take care of all those signs into account, right? Now, today, what I'm going to say here, what I told you is, don't worry about the sign, add them together blindly like this, okay? Suppose you are talking, because you have only one theta, right? So what are the impedance related to this theta? You have K, you have ds, you have js squared. Add them all together without taking any sign into account. How cool is that? Then multiply that by theta, this theta, then equal to, so external torque. How many, what is external torque there? We have only one external torque. If we had two, then we will add here another two. This always works. If I had taught this trick in the beginning, you wouldn't even pay attention to these guys, this rule.
So direction really doesn't matter?
No, in this case, yes. So direction does matter. Remember how we got this one? We
Right.
have to pay attention to direction, right?
Mm-hmm.
So what we end up getting is this. What I'm trying to say is, this is what we always end up getting. So what is the degree of freedom here? Theta, right? Okay, theta goes here. Degree of freedom is theta. Okay, so multiply that theta by, what are the impedance related to that theta? Theta is degree of freedom, right? Theta is degree of freedom. What are the impedances related to this theta? You have js square, you have ds, you have k. Don't think anything about the sign, just add them together. How cool is that? Then what will be on the right hand side? Sum of all the torque. We have only one. That's it. Without doing anything, we got the final answer. Boom. One step. Good news, this always works. This is the rule. Sum of impedances connected to the motion at theta times theta. See, this theta and this theta, they are same. Keep that in mind, okay? This theta is this theta. Then sum of applied torque at theta. These all three theta. I think if you do one more problem, then you will appreciate it. You're not so in a mood of to appreciate me right now. So let me give you one more example. Hopefully that will make me happy. So let's do another problem here. So now I don't worry about any sign here. Remember, we had to do clockwise, counterclockwise, those kind of thing. I don't worry anything about it. So now I'm here. I'm here, right? Okay. What is the nearby? So this is for theta 1, right? What are the adjacent components to me? These components are adjacent, right? Okay. Now, what is the sum of impedance? So now what I said is just write theta 1. Write theta 1. Okay. Then what is this guy? What is this guy? D1S. What is this guy? KS. What is this guy? J1S square. What I said is, don't worry about the sign, just add them together. J1S square plus D1S plus K. Add them together. Okay. Then, since we have 2 degrees of freedom here, unlike in the previous slide, what we do here is, then we take the sum of impedances between theta 1 and theta 2. What is the sum of impedances between theta 1 and theta 2 here? These two. What is the impedance between these two? So that will be, because you already have theta 1 here, this will be theta 2, okay? Keep that in mind. Then, what is the sum of impedance between these two guys? Ks. So let me put Ks here to save my space. Equals, so what is the sum of applied torque at theta 1? At theta 1, how many torques are there? Only one, T. Okay? So, how do I choose this negative sign then? So there is always negative sign if there is in between. Remember this between means negative. So I have this guy between, in between. That's why this is negative. What did I do here? I should have said theta 2. Okay. Now let me do the, now I'm switching to this position now.
Is it KS theta 2 or K theta 2?
K theta 2, right?
Okay.
Because K doesn't, sorry, this K doesn't have S, right?
Oh, okay.
Remember I made a mistake before?
Oh, right. Yep.
Okay. So now you are here. Now you are going to deal with theta 2, right? You are here. So what is your surrounding? This is your surrounding. Okay. Now, so give me the theta 2. Because you are talking about theta 2, right? What is the sum of impedances? J2 S square, D2S, and K, right? J2S square plus D2S plus K. Then what is the common? What is connected in between theta 1 and theta 2? That will be minus, right? In between will be always minus. So what is connected in between? K. Since we already have theta 2, that K will be theta 1 now. Because you have to have both theta 1 and theta 2 in each equations. Then what is the torque? No torque, right? Guys, makes sense? Not really. I should have avoided this.
It makes sense to me.
Okay. So if it makes sense, just help me here now, okay? Let me repeat this one more time. If it makes sense, that prove it. I need your help here. So, okay, let's do theta 1 again. So here. So give me the equation here for theta 1. At theta 1, what is the equation? Who can help me here now? Anybody?
Would it be JS squared plus DS plus K? All within parentheses with theta 1.
Why theta 1?
Because it's asking for the sum of impedances connected to the motion at theta 1. So we're just concerned with theta 1 right now?
Yeah, so yes, theta 1. So this in between thing, because we are talking about theta 1, right? So theta 1, okay, we are talking about theta 1, that in between thing comes and that carries the opposite one. So opposite of theta 1 is theta 2. Okay? In between thing always take the opposite. Okay, so let me mention here. In between, this in between always take theta 2. In between always take theta 1. See, it's always take opposite. If you are talking about theta 2, then that will take the opposite, which is theta 1. If you are talking about theta 1, that will always take the opposite, which is theta 2. Because this is for theta 1, right? We are just talking about theta 1 right now. See, this is our circle. This is the circle for theta 1. Meaning you are talking about theta 1. Then in that case, your in-between thing will be theta 2. If you talk about this circle here in the next step, then that in between thing will be theta 1 in that case. Okay, so go ahead. Thank you. So then what next?
Minus
Remember?
J, is it J2 S squared and then D2 S?
No.
or add
Okay,
this-
so we have done with theta 1. Now we have to do the theta 2, right?
Right.
For the theta 2, this is the in between. So meaning, what is the, because we are at theta 1, what is the
Oh,
thing between theta 1 and theta 2?
I see. Okay.
Just K. Just K, right? In between?
Oh, so wouldn't J1 be mixed in with that?
No, because between theta 1 and theta 2, there is only, the breeze is, there is only one breeze between theta 1 and theta 2. There is no two breezes. There is only one breeze between theta 1 and theta 2, which is this K.
Okay.
Does it make sense? Yeah,
Yeah.
You can say no.
I guess I'm just not understanding why we wouldn't. I guess because of the way it's laid out is that theta 1 is to the left of J1. I guess it kind of looks like J1 and K are in between the two of them.
Oh, no. What I'm saying is, when I say theta 1, I'm talking about this bubble. Bubble of theta 1.
I see.
Okay? Oh, that is the confusion. Yes, this is I'm talking about the bubble. This whole entire bubble. This is theta 1 bubble.
Okay.
So K theta 2 equals to, then what is the sum of applied torque in that bubble?
TS.
Just T, right? TS. Exactly. Now let's shift the bubble now to the right. Let's shift the bubble to the right, and that is the bubble of theta 2. Because you are staying here, right? You are on J2 now. Okay. So what is next to you? On the left you have a spring, on the right you have dashpot. Okay. Now since this is the bubble of theta 2, right? Let's deal with theta 2 first. Bubble of theta 2. Let's deal with theta 2 first. So what is the sum of impedances connected to the theta 2? Let's do that first.
J2S squared plus D2S plus K.
Exactly. So then now give me the in-between thing. Since I already have theta 2, now next will be theta 1, right?
Just minus K. K theta.
Minus K, exactly. So in between always takes minus, okay? In between always takes minus. Then what is the sum of applied torque?
0.
0. Remember this trick even works for the electrical circuit. If you look at your book, the book has done this kind of thing a lot. But I didn't mention it there because if I had mentioned this, you wouldn't pay attention to minus and plus sign, never. Because this is so easy. It doesn't make sense now.
Yeah.
Like for me, I understand how like you like drew it up, but that's kind of all I understand about it. I just understand like, how you drew it up, if that makes sense. I don't know how it's like applied.
Oh, okay. So. Okay, let me ask you then. So, okay, that's fine. So let's start over again. Because I want you to do it. I want you to understand it. There's no.
Hello. I mean,
Okay, let's start with the bubble theta 1 because this is very important. And if you understand this, You love this course.
So I understand like what's in theta 1.
Okay, give me then. What is in the theta 1?
And so this, my question here, one quick question before that. So the sum of impedances connected to the motion at theta 1, that's what we're trying to solve. And try to, like, that's the equation we're writing down.
No,
right?
because we have theta 1 and theta 2, right?
Mhm.
So how many equations do you think we should have?
How many
2.
what?
How many equations do you think we should have?
Oh, okay, two.
2. So
Yeah.
that's why we have to make 2 equations, right?
Mm-hmm.
So from this rule, you get 1 equation. From this rule, you get another equation.
Okay.
That's what I'm trying to say.
Okay.
So
I
this
got you.
equation, okay, this equation, the previous one is coming from bubble,
Mm-hmm.
theta 1 bubble. This is coming from theta 1 bubble, and this is coming from
Theta 2.
theta 2 bubble.
Okay. That makes sense though. Yeah, I understand it.
Okay, good.
Yeah, I got you. Thank you.
All
Appreciate
right.
it.
Guys, any other question? All right. All right. Because I need this in the for chapter 2.7. That's why I so focused on that. Okay, I need this trick. Now we're going to do the transfer function for the system with gears. Okay, it's the same system, rotational motion, right? You have the same rotational motion, remember? You have, I don't know, you have a dashpot, you have the dashpot, you have the spring, right? Then you have the inertia, but now this is connected by gears, like this. Remember, when you have the real system, then you will have a motor, right? In robotics, we talk about DC motor a lot, DC motor, right? So you have a DC motor, and that DC motor will act on the gears, right? Remember this gear, these two are gears. See, this just, I made just 2 vertical lines. So this longer one is this gear here. Longer one is this, and the shorter line here is this gear. Okay? So that's how you represent gear in this course now. So one line short, the other one longer. But actual picture is this. This is short, this is long. Okay, this is short gear, this is long gear. Okay, so if you have, let me say it again. If you have a DC motor connected to gear, which instead connected to inertia, dashpot, dashpot, and spring. In this case, how do you solve this problem? That's what I'm trying to say. Okay, so it's the same rotational system, but we have extra there. What is the extra? Extra is gear. So why do we need gear? Because gears are useful to get the mechanical advantage, right? So you know mechanical advantage. Okay, let's say, so of course you have seen gears, right, in a bicycle, right? So this is the easiest example, bicycle. You have a bicycle. You have one gear on the rear. This is rear wheel. This is rear. This is front. Okay, you have 2 gears here, front wheel and rear wheel. So so what is F times D in translation motion? Force times displacement is work or energy, right? Work or energy. So in the case of rotational motion, this F becomes T, D becomes theta. So energy equals T theta. That's how you define energy in rotational motion, right? Energy equals T theta. Energy equals T theta, right? This is your energy. So what is the conservation of energy? T1 theta 1 equals T2 theta 2. That's the conservation of energy. So if you take the derivative of theta 1 and take the derivative of theta 2, meaning taking the derivative on both sides here. Take the derivative on both sides. Then you end up getting this. Because the force doesn't change over time. So this is constant force or constant torque in this case. So only thing that changes is the theta, right? When something rotates, theta changes, right? Okay, constant torque, but theta changes. That's why you have the derivative theta 1 and theta 2. So now from the conservation of energy, you got this equation. So this tells us something very important, okay? So what does this tell you? If this is, what is this called? Speed, okay? If you lower the speed, then your T1 should go high because your product should stay the same. Does it make sense? Suppose your T is 3, this is 4. Suppose you have T is 4 and this is 2. This is 3, right? Suppose you decrease theta. You decrease theta to 2. Then what should be this one? This should be 6. Isn't it? Okay, if one increases, the other one decreases, right? So in other words, in the low, when the speed is low, then you get higher torque. When the speed is high, you get the lower torque. Okay? And you can represent that gear system as shown in the figure here. Okay? This is the input gear. This is the output gear. The big one is output gear. And input gear has the radius R1, as you can see here. Input gear has the radius R1. Output gear has the radius R2. Input gear has number of teeth, N1, number of teeth here, N2. And for the input gear, the torque is T1. You know, the angle displacement is theta 1. For the output, the torque is theta T2, and displacement is theta 2. Okay. Now in this case, I'm going to derive one thing here. So I'm deriving this formula here. I'm going to derive. So R1, let's say, by the time, okay. So what is happening is this guy is, see, this guy is moving or rotating onto this guy, right? Input is rotating onto output. You see that, right? Okay. So here input, when this is theta, let's say this is theta. This is theta here. From here to here is theta 1. And from here to here is theta 2. This is your, let me choose different color here. So this is your theta 1. This is your theta 2. Okay. So what is this guy? From here to here. How do you represent this guy? Anybody help me, please? Can I write this guy as R2 theta 2? Can I write this guy as R1 theta 1? This arc length. I'm talking about arc length. Can I write this R1 theta 1 and this one R2 theta 2?
Quick question. So the R is starting, so arc length is what you're saying, real quick.
Say it again.
Is R arc length is what you're saying? Is that what you're saying?
Yeah, this is the arc length, right?
Okay.
This is the arc length. This arc length is R1 times theta 1. This arc length is R2 times theta 2. Does it make sense? So do you think by the time this guy goes from here to here, this guy goes from here to here, they are equal? Remember how the gear work, right? One slides over the other, right? So by the time this point reaches here, this point reaches here, shouldn't they be same? They're exactly same, right? That's why this arc length should be equal, meaning R1 theta 1 equals R2 theta 2. Question. Guys, any questions so far? So can I write this guy as this? Can I write this guy as theta 2 over theta 1 equals R1 over R2? Can I write this one? Now, also number of teeth here. So what I mean by teeth? So these teeth here, these teeth here, let's say these teeth, there are 50 teeth. How many teeth are there? Let's say there are 10 teeth. Okay, I don't know. This is just a guess, right? So the number of teeth is proportional to radius. Smaller radius, less teeth. Bigger radius, more teeth. That's what I meant. Number of teeth proportional to radius. Meaning N equals K times R. Okay? In other words, N1 equals KR1, N2 equals KR2. If you divide both, then what do you get? R1 over R2 equals N1 over N2. So that's why I can say write R1 over R2 equals N1 over N2. So far, so good. Okay. And also we know that T1 over T1 theta 1 equals T2 theta 2. We know this also, right? So what do you get from here? What is your theta 2 over theta 1 from here? T1 over T2. Now also this guy equal to T1 over T2. Look at that. We have a huge relation here. Relationship between many, 4 different parameters or variables rather. Does it make sense? So this is very useful relation. We proved it. Okay. So before I should have written this picture in the next slide. Okay, before I come to this slide, this picture, I'll go to next slide and come back. Okay. Okay, so far so good, right? Let's talk about the real system, mechanical impedance driven by gears. Let's talk about the real system now. So we know fundamentals about gears, right? So what is the fundamental we know so far? So this is the relation. Keep this in mind. This is always easy to remember. So theta 1, theta 2 over theta 1 equals R over R, N over N, T over T. So this is 2 over 1. Everything is 1, 1, 1. 1, 1, 1 on the top, 2, 2, 2 on the bottom. It's that easy to remember. Okay, you have theta 2 over theta 1 equals R1 over R2, N1 over N2, T1 over T2. Okay, now let me go to this slide here. Suppose you are going to solve this problem here. This problem. This is your problem. So what do we have here? You have the dash spot. This is the dash spot. This is the spring. This is inertia. And this system is connected to T1 via gears. Okay, these are gears. See, this is small gear. And this is big gear. There are 2 gears. Okay, and this gear has N1 number of teeth, and this gear has N2 number of teeth. Okay. Now, what is the torque applied to this gear? Because you have to remember when you ride the bicycle, right? You have to apply the torque by using the pedals, right? Bicycle pedal. So that's what torque is. You apply the torque, and it starts spinning. Theta 1. Suppose you apply torque here, and this gear starts spinning, rotating rather. So with theta, it starts rotating. So theta 1 is the angle during the rotation. Okay, that's what I meant. Similarly, at the same time, the gear having N2 number of teeth, okay, it rotates such that during that time the angle is theta 2. When angle is theta 1 here, angle here is theta 2. When you rotate gear 1 by angle theta 1, at the same time, the gear 2 will be rotated by theta 2. And you rotate gear 1 by using T1 torque. Then your system has J, D, and K. Okay. Now the thing is, so I'm going to do very important things. So I want you guys pay attention very carefully here. Okay, please. This is very important. Okay. So what I'm trying to do here is I'm trying to, looks like this has 2 degrees of freedom, right? Theta 1 and theta 2. Looks like it has 2 degrees of freedom, right? But the thing is, they are tied together by gears. Look at that. This gear and this gear, there is no slipping in between them. The gear do not slip. They don't slip. So there is no slipping between these 2 gears in that case. So theta 1 can be related to theta 2. And there is no 2 degrees of freedom anymore. In other words, the gears are tied, the system tied together by gears. In that sense, there is only 1 degree of freedom. You can call, okay, the degree of freedom is theta 1 or degree of freedom is theta 2. You don't have to write 2 equations. Okay. Now, if it is, suppose So I'm telling you guys, okay, I'm asking you guys to find, okay, I'm asking you guys to find theta 1 over T1. Suppose find the transfer function in this case, right? I want you to find the transfer function T1, theta 1 over T1. Now, how do you do that? That's what I'm going to teach here, okay? So whenever you have gears, you write the equations like how many degrees of freedom we have? You have just 1 degree of freedom, right? Let me call my degree of freedom with theta 2. You can start with theta 1 also. You get the same answer. You can consider theta 1 is your degree of freedom or theta 2 as your degree of freedom. For now, I'm trying to consider theta 2 as my degree of freedom. Now, if I consider theta 2 as my degree of freedom, what is the equations you write? Remember, if you have one equation, what is the formula? Right? Sum of impedances, theta equals T. That's all. So, what are the impedances here? So, what are they? We used to have JS square. Guys, help me here. DS plus K, right? But the thing is, we're not just talking about these 3 things, but we have to take this guy into account. That's why instead of writing J, D, and K, I simply write J, E, D, E, and K, E. What does that mean? That E refers to equivalent. So now the thing is, you already have the equation. Your machine is ready. This is your machine. Now you need to figure out your raw material here. Your machine is ready to go. Now figure out raw material. What is JE? What is DE? What is KE? So this is theta 2, by the way, right? This is theta, this is T2. Okay. Now, okay, all right. So you need theta 1 over theta 2, right? So your goal is theta 1 over theta 2. Sorry, theta 1 over T1. Now you started with theta 2 and T2. Because I want you to figure out this. But the thing is, I started with theta 2, T2, right? Okay. Now, how do you change your theta 2 to theta 2 to theta 1? How do you change your T2 to T1? And how do you find your JE, DE, and KE? So figure out this, figure out this, figure out this, figure out this, and figure out this, then you are done. All right, so let's begin with theta 2 and theta 1. Let's figure out these two first, theta and T. What is the relationship between theta 2 and theta 1? What is the relationship between T2 and T1? Let's figure that out, okay? To figure that out, we use this example here. So if you go from theta 1 to theta 2, if you go from theta 1 to theta 2, what do you do? Your theta 2 is N1 times N1 over N2 times theta 1. You can get this from here too, right? You can get this from here too. It's the same thing. But I have the picture here. Okay, you can do this or that. That's fine. When you go from theta 1 to theta 2, you multiply by N1 over N2. See? If you want to find theta 2, multiply theta 1 by N1 over N2. If you want to go from T1 to T2, you multiply by N1 over N2. So meaning T2 equals n1 over n, oops, n2 over n1 times t1. So you can get this from here too. See, it's the same thing. This gives you this. But why did I have this picture here? Because this is very important. Because this is important for other purpose too, okay? Why is it important is, so I call this source. Theta 1 is source. I call theta 2 the destination. So then here, this is my source. This is my destination. So in the case of theta, if you go from source to destination, then multiply by n1 over n2. Okay? But the next one is very important to me. This one is very important to me, okay? Let me erase this theta 1 now. So you understand this. Now, I'll explain this this thing here. Suppose you are going from T1 to T2. You want to go from T1 to T2, meaning T2 is your destination, T1 is a source point. Then you have to multiply by destination because N2 refers to destination, right? And N1 refers to source. You always divide destination by source. Destination by source. If you go from T1 to T2, keep that in mind, okay? If you go from T1 to T2, you multiply by destination by source. If you go from T1 to T2, multiply destination over source. So this is your multiplication factor. Your multiplication factor is N2 over N1. Multiply by this. Destination over source. This will be very helpful for you guys. So keep this in mind, okay? Destination over source. All right. How do I use this here? It's not clear yet, right? So let me make it clear here. Now, having said that, so how do you change your theta 2 now? So what is your goal? Theta 1 over T1. Now, can you guys help me here? You have to help me here, okay? Are you going from theta 2 to theta 1 or theta 2 to theta 1? Oops. Theta 1 to theta 2. Guys, help me here. I'll be waiting.
Theta 2 to theta 1.
Exactly. I'm going from theta 2 to theta 1. So, meaning you are going from T2 to T1, T2 to T1, right? You can say T2 to T1. So you are going from T2 to T1. You are going from T2 to T1. Okay? So what is the relationship between T2 and T1? So what is the relationship between T2 and T1? This is the thing, right? So replace this guy by, okay, now my T2 is replaced by this. My T2 is replaced by T1 N2 over N1. Does it make sense?
Yes.
Okay. Now, so how do I, now in this case, how do I represent my entire system then? Let me erase it. What do I mean by that is this. Now I started with this system, right? Remember, I started with this system. Now I changed my, I went, so when I went from T2 to T1, what did I do? T2 to T1, right? Here. Oops. Okay, so T2 is here. So I'm going from here to here. That's why I'm writing now. I can ignore this because I'm just dealing with theta 2, right? I'm just dealing with theta 2. That's why you don't have to write this guy here. You don't have to write this guy. This is gone because you already wrote your T2. By the way, this is T2, okay, here. This is T2 here. You wrote your T2 in terms of T1 already. Do you see that? You already wrote your T2 in terms of T1. You don't need this anymore. This guy is vanished. This is vanished. That's what I have here. Look at that. This guy vanished. You just have T2 replaced by T1 N2 over N1, and you just have theta 2 here. See, I simplified my circuit. I don't have this anymore. This guy is gone. This guy is gone. I just have this much here, which is this. Okay. Now, instead, if you want to write, okay, if you want to write in terms of theta 1 then, instead of theta 2, so let me simplify here, okay? I'll come back to this picture later on. So I have this already, right? So this is your JE, this is your DE, this is your KE, theta 2 equals T2, this is T2. So we have this now. Now my claim is, so let me, because I started with J, K, and D, okay? I have J, D, and E, K. Then I'm changing my theta 2 to theta 1. How do I do that? If you change my theta 2 to theta 1, this is what I get, right? So now this is the conversion here, this to this. Oops. This is actually T2, right? This is T2. So from T2 to here, this is one conversion. And theta 2 to theta 1, this is another conversion. Now I have two conversions. So now can I rewrite this guy as this? Can I rewrite? Can I rewrite this guy as this? So let's multiply both sides by N1 over N2. What happens? You multiply both sides by N1 over, this cancel out. So what I'm left with? N1 is squared, N2 is squared, right? See that? You see that? So here, this guy now, let me write this guy now. JS squared N1 over N2 squared plus DS N1 over N2 squared plus K N1 over N2 squared. This entire thing multiply by theta 1 equals T1. This is my conclusion. So this is my conclusion. Now I will define what is my JEQ now. So this is my JEQ. My JEQ is JEQ, or simply E, is JS squared N1 over N2 square. Now similarly, help me, what is my DEQ? DEQ is D N1 over N2 square. Then what is my KE? KE is simply K N1 N2 square. Now I define my equivalent J, D, and K. Conclusion. Okay. Now the conclusion is, this is very important. Okay, please pay attention to it, please, everybody. This is the conclusion is very important. So here, I'm going from theta 2 to theta 1, meaning I'm going from here to here. So when you are going from theta 2 to theta 1, what you are carrying with me? What you are carrying with you? You are carrying J with you. You are carrying D with you. You are carrying K with you. Yes or no? So, but you are carrying this and you are jumping over the gears here. This is the gear. You are jumping from theta 2 to theta 1. You understand? When you jump from theta 2 to theta 1, then you have to change this J, you have to change your D, we have to change your K. How do you change it? When you change your J, you have to take destination over source square. Destination over source square. What is the destination here? N1 is the destination, right? Source is N2. You are going from theta 2 to theta 1. That's why theta 1 is your destination, theta 2 is your source. Okay? When you carry J from source to destination across the gear, then you have to multiply by destination N over source N squared. That's what my N1 over N2 squared. Does it make sense? Remember, destination over source whole squared. That's how you multiply. Okay? So similarly, not only you are carrying your inertia, right? Not only you are carrying your inertia, but also you are carrying your D. Look at that. You are carrying also the D across the gear. When you carry your D across the gear, in that case also, you do the same thing. Destination over source. Destination N1, source N2 squared. Similarly, when you carry your K over the gear, you do the same thing. You multiply by your K by destination over source squared. Then rest is easy, because with that, you go to theta 1. Now you have T1. Boom. Guys, question here. I'm ready to answer the question now, right now. Guys, I need some comment here. Lucas, can you please comment something?
So far I'm pretty set on everything.
Okay, very good. Emery?
Think I'm getting it.
Okay, Jane?
Yeah, pretty sure I'm good.
Okay, Nick?
Yep, looks good to me.
Saad? Hello? Saad?
I don't think he's here anymore.
Yeah, I know. He's yesterday also I called him many times. He didn't hear me. Is he taking nap? Hi, Saad. LJ? Yeah, because I can see your face. Okay, I can clearly read your face. Okay, that makes me happy. Very good. All right. So this is the rule. See that this big rule, number of teeth of gear on destination shaft, number of teeth of gear on source shaft is squared. That's how you transfer across the gear. Okay, this is the rule we'll be using again and again. Okay, guys, are you guys ready for the example? All right. Okay, now our goal is to figure out transfer function. So G theta 2 over T. Now help me here. What is your, okay, what is your theta 2? This is your theta 2, right? This is your theta 2. And I call this is theta 1. The book doesn't say so. This is the problem from the book. Example, actually. This is the example. No, not the example. This is the actual problem. Okay. So your book says skill assessment exercise 210. Okay. This is 2.10 from the book, page number 69 in the print version. Unfortunately, in the online version, it doesn't have any page, right? But in the print version of the book, it is from page number 69. So example, exercise 210, okay? So we need to find theta 2 over T, theta 2, okay? Keep that in mind, theta 2, okay? Now, let me see what do we have in the picture here. You have, what do you have? You have the inertia of 1 kilogram meter square. I call simply J. And this guy is rotated with the torque T. And during the rotation, you have theta 1, which I call theta simply because I want to match the notation here. So T1 is T, theta 1 is theta. That's what I'm trying to match, okay? So then you have the dash spot, okay? Then you have gear here. This is input gear. This is the output gear. So output gear has 50 teeth. Input gear has 25 teeth. Similarly, the output gear is connected to, oops, what is this called? Help me. What is the name of this guy? Spring. Okay, connected to spring. Then this spring has torque T2, right? Under the torque T2, and the angle is theta 2. Even though we see there are two theta, we know there is only one theta, right? Because they are connected by gears, right? So since they are connected by the gears, even though it seems that there are 2 degrees of freedom, but practically there is only 1 degree of freedom, okay? Now, our goal is to find theta 2 over T, meaning theta 2 over this T here, this T. Okay, now the thing is, how do you do this? So one equation, I have a machine here, right? Because you need the theta 2, keep this in mind. You need theta 2, right? That's why you need the equation in terms of theta 2. Boom, there is no doubt. This is what you need. So what is the thing here? JE S square DE S plus KE. See, your machine is ready. Now you have to figure out all your raw material now. So do you guys know how to build your machine in the beginning? So this is always there. JES square, your machine has one part constant all the time. JES square, DES plus KE, that term is always there. Then since your G has to be in terms of theta 2, you multiply by theta 2, then equals T2. Theta 2, T2. Look at that. That's your machine. Your machine is ready. Now, figure out the raw material now. What are the raw materials? Meaning, what is your JE? What is your DE? What is your KE? What is your theta 2? Theta 2, you don't have to change it because you have to do it in terms of theta 2. So you have to change the theta T2 in terms of T1. Okay? It means I use this formula here. That's what I did. This is my machine now. They're exactly the same thing. Now, guys, help me here. What is your JEQ?
N1 over N2 squared.
Okay, now, so theta 2, you are writing in terms of theta 2, right? So you have to do this, everything, you have to bring it to theta 2 because your equation needs theta 2, right? Get these guys to theta 2 now. Bring it over to theta 2. Jen, can you help me? What did you say? I'm sorry.
Well, I was thinking it would be N1 over N2 squared. I don't know.
Yeah, so remember what is your rule here? Number of teeth in the destination shaft over number of teeth in the source shaft, right? Then it's squared. So now you need theta 2, right? You need theta 2. That's why you want to change your all your theta 1, 2. You want to carry it over to theta 2. Bring it over here. That's your destination now. Now this is your also destination. So bring your D over to theta 2, J over to theta 2. Theta 2 side, other side. Bring it to the other side. Because you need theta 2, right? All right. So you need theta 2. That's why I bring it over to the next side. Now, when you bring your J to the other side, what do we get? So you have to bring the J. Let's bring your J over to theta 2. So when you bring it over to J to theta 2, what do you get? JE equals, what is your destination? So you have to multiply destination by source square, right? What is your destination? Help me. Destination N2. Your source is N1. That's your JE. See, your J becomes J times N2 over N1 squared. Meaning your J is amplified by 4 because your N2 is 50, N1 is 25, then times J, which is 4J. See the magic that gears has done, right? It amplifies your inertia by 4 times. Okay, that's awesome. So similarly, when you bring your D over to theta 2 now, again, what do? It's the same rule. DE equals destination over source square times D. Your D gets multiplied by destination over source square, meaning number of teeth in the destination on the destination shaft over number of teeth on the source shaft. So again, this is your N2 over N1. So what is that again? 4 times D. Actually, D is also given, right? So, okay, let me keep it like this for now. Okay. Now help me with the K.
So would we not apply the transformation to K because it's on the destination side?
Exactly. You made my day. Thank you, Jane. That's very good question. Comment. Okay. So then K is K. We don't do anything because it's already in the destination side. Okay. Now, let's write this down then. So what is your J? J is 1, right? So you simply get 4 here. Your D is 1, you simply get 4 here. What is your K? K is simply 4. So what do you get here? 4s squared plus 4s plus 4 theta 2 equals T2, right? Now, what do you have to do with the T2 now? Now, you are almost there, right? You have theta 2, but you have to replace your T2 by T1 because T1 is T, right? See, this is your T1 and T1 is T. So what is the rule for T2 and T1? You know that rule, right? See, so this is your rule. Oops, what is the rule? So this guy, right? Remember this guy? So what is your T2 equals? Help me. What do you get from there?
It would be equal to N2 over N1 times T1.
T2 equals N2 over N1 times T1, right? So what is your N2? 2. The T1 is T, right? So that's how I got 2T here. Now, can you find theta 2 over T from there? Guys, I'm done, okay? Bear with me just a second. So now what is your theta 2 over T? Can I say 1 over 2 s squared plus s plus 1? Because this guy, he had 4 here, right? It factored out 4, s squared plus 4 plus, oops, s plus 1 theta 2 equals 2T, right? Then what is your theta 2 over T? 2 over 4, right? This is 2 over 4. 2 over 4. Then you can simplify that to 1 over 2, right? 1 over 2. So that's your answer. Boom. This is your answer. So this process is called reflecting impedances, okay? This process is called reflecting impedance. Reflecting impedance, okay? Sometimes we reflect from left to right. Sometimes we reflect from right to left, right? So depending on what you need, you have to reflect impedance one way or the other way. But whatever you do, you get the same answer, but one route will be longer than the other route, okay? You should get the same answer either way, but one route might be longer than the other route. Because ultimately you have to change into theta 2, theta 1, those kind of thing. You have to do the change there, right? So eventually, so only it's the matter of longer or shorter route, okay? So either way you get the same answer, but I would prefer the shorter route, right? So everybody does that. So that's why I decided to write in terms of theta 2. Instead of writing in terms of theta 1, okay, instead of writing in terms of theta 1, I wrote in terms of theta 2 because I need theta 2 here. Okay, but I would have got the same answer if we had started with theta 1 and theta T1. But I have to do the longer thing here. Eventually, I have to change back to theta 2 again, okay? So that's the longer route. But you get the same answer either way. It's the same question, you know, same problem. So unless you have any other question, I'm done for the day.
I'm all set. I have to go to my next class.